In this presentation, we're going to be looking at graph traversals or graph searches. And there are two very popular algorithms for searching in graphs. One is referred to as a breadth-first search, and the other is referred to as a depth-first search. If you recall from our previous work, we have implemented a graph as a list of nodes, simply just as a list of strings, and an adjacency matrix that tells us the edges or the paths. And we implemented the adjacency matrix as just a dynamic two-dimensional array, and we use the standard template library as vectors, so we made a vector of integer to implement this adjacency matrix. So in this particular presentation, we're going to look at the algorithm for a breadth-first search and trace through that algorithm to see if we can do a traversal or see how it works to find a particular path. Recall that in our implementation of the breadth-first search, or our implementation of the graph, we just had a node list that was a list of strings and an adjacency matrix that was a dynamic two-dimensional array of integer. So the algorithm that we find, we may have to modify a little bit because our implementation of the graph is like this. The algorithm that I'm going to start with here is, I found this in Wikipedia, and G is the graph, start V is the start node. They have a queue, they use a queue, and they have nodes being labeled as discovered and nodes having parent-child relationship. Since our nodes are just simple strings, there's really no easy way we could label them as discovered or label them as having a parent node. So I'm going to add two additional data structures to use in this algorithm. One is just a list or a set of nodes that we've discovered or visited. And the reason for this is so that we don't backtrack or create a loop in our graph. We need to keep track of where we've been so that we don't revisit nodes and create a loop or backtrack. The other thing is I'm going to create a hash table or dictionary, or in C++ an unordered map that will map a child to a parent node. So let's see how we can do this, how this algorithm might work for us. And I'm going to use this particular graph that we've seen before, and I'm going to say that the start node is F, we want to start from F, and the end node is A. We want to find a path from F to A in this graph. So A is going to be the goal that they talk about here in the algorithm. So let's see how this might work. Let Q be a queue, so here's our queue with a front and back. And then label start V as discovered. So the start node needs to be added to the discovered list. So we could just quickly look up in this list to see if a node in the future has already been discovered or visited, so we don't revisit it. And then step 4, we want to enqueue that start node. So we're going to put that starting node into the queue. And since the queue is empty, the back and the front of the queue are going to be the same. Now we're going to ask the question, is V the goal? Oh, we forgot to set V. So, So we've, step 4, we enqueued the starting node, and then we didn't do step 5. So step 5 says, is Q not empty? And that's true. Q has something in it, so it's not empty. And then we say V equals Q dq. So this removes F from the queue and puts it in V. So now we're here at step 7, is V the goal? And F is not the end node, which is our goal. So we don't have to worry about doing this. Now this for loop needs a little bit of translation because they're trying to do for all the edges in the graph that go from V. So the translation of this is all the edges in the graph that go out from V. So in our case, we only have one edge in the graph that goes out from the current value of V, which is F. So that's F to D. So we only really have one to consider. And V is F, and W in this case is going to be D, the path from V to W. We only have one from F to D. So they say then that, so W then is going to be D, and then we ask the question if W is not labeled as discovered. So in our case, is W, the value of W, in our discovered list? So D is not in here, so that's true. It's not been discovered or visited yet. So now we're going to label W as discovered. So in order to do that, we just put D in our discovered or visited list. And now they're setting up this parent-child relationship. So they're saying that the parent of W is going to be equal to V. So what that means is that the parent of D is going to be equal to V or F. So W's parent, D's parent, is going to be equal to V, which is F. So D's parent is F, so that's how we put that in our parent map. And this is setting up kind of like a trail of breadcrumbs that we'll be able to follow and find the path a little bit later on. And then we need to NQ W, so we need to put W in the Q, so that puts D into the Q. So now we're finished with the end of the loop. We go back up here and it says for all edges from V to W. Well, all edges from V was just V is F, so we only had the one edge. So now we're actually finished with this for loop, and we need to go back up to this while loop. And the while loop says while Q is not empty, and Q is not empty, it has a D in it, we want to NQ. So what that means is to take D out of the Q and put it in V. So we're going to DQ and put the value that was in the Q, D, into V. And while we ask the question, is D the goal? And it's not. Our goal is A. So now let's say from all edges coming out of D. Okay. Well, those edges are D to F and D to E. So let's consider D to F first. So for all edges, V to W, so that's the first one we're going to look at is D to F, and we just have to remember that we have to do D to E also. Do. So if W is not labeled as discovered, well, it turns out that F is in the discovered list. So this if test is going to fail, and this is where we're avoiding backtracking, going back to a node that we've already visited. So this fails. So now we go back, we skip all this, go back to the for loop, and it says for the next edge in the graph that goes from D to somewhere, and that one was D to E we haven't done. So we're going to consider D to E, and then if W is not labeled as discovered, so E is not in the discovered list, so they want to label it as discovered, so we add it to the discovered list, and then set W's parent as V. So that means E's parent is going to be D. So we put that in here like this. E's parent is D. And now we're going to NQ W, which is E. So we're going to put W in the Q. And the value of W is E. So we're putting E into the Q. So now the next step is we go back up to the for loop, and for all the edges from V, so for all the edges from D. So we've already considered D to F, we've already considered D to E, so we're done. We've done all the edges from D. So then we go back up to the while loop, and it asks while the queue is not empty, and the queue has E in it, so it's not empty, and we want to dequeue that. So we take the value from the queue, remove it, and put it in V. So we finished step 6 here. And we ask the question, is V the goal? V is not our end node, so it's not the goal. Now we're going to consider all edges in the graph from V. Well, if you look in our graph, all the edges in the graph from the value of V is E. All the edges in the graph from E are E to D and E to B. So again, we can start by considering maybe E to D, and we ask the question, is W not labeled as discovered? Well, W is D, and it is in our discovered list, so this if test is going to fail, again, keeping us from backtracking. So now we skip all this, go back up to this for loop, and we look for the next edge from V, which is the current node V, which is E. We already considered E to D, so the next one to consider is E to B. And then we ask if W is not labeled as discovered. B is not in the discovered list, so this is going to be true. We label B as discovered. We set up the parent relationship. So this parent relationship is going to be W parent equals V. So B's parent is E. So we're going to mark that in our parent map. B's parent is E. And then we're going to enqueue W, so we're putting the B into the queue. So now we go back up to this for loop, and have we considered all the edges from B, which is E? Well, we considered E to D and we considered E to B, so we're finished with this for loop. So now we go back up to step 5, which is while the queue is not empty, and the queue has B in it, so it's not empty, we dequeue that, so that B goes here, and we remove it from the queue. And then after the dequeue, we ask if V is the goal. Well, V is B, and that's not the goal that we're looking for, so we want to keep going. For all edges from V to W, so all edges from B, so B has three edges going out of it. We have B to E, B to C, and B to A. So we have to remember that this for loop here is going to iterate 3 times. One for the B to E, one for the B to C, and one for the B to A. So let's consider the B to E first. It doesn't really matter what order we do it in. We come down and ask this question, if W is not labeled as discovered, well, we notice that the value of WE is in the discovered list, so we have already visited it, so you don't want to do it again, so this if test will fail. We go back up and look at the next edge. Let's look at C. If C is not labeled as discovered, so C is not in the discovered list, so we're going to label C as discovered. And then we're going to set up C's parent as V, which is B. So C's parent is B. And what this says is that how did we get to C in our search? We got to C by coming from B. The parent of C was B in this particular search. So we're going to label that. W's parent equals V. W is C, and V is B. So C's parent was B. And then we're going to enqueue W, which is C. So we're going to put the C in here. So we go back up for all edges from B. Have we considered all edges from B? Well, we considered B to E, we considered B to C, but we haven't yet considered B to A, so that's the third iteration of this loop that we need to do. So there's B to A. And we ask if W is not labeled as discovered. Is W labeled as discovered? No, it's not. It's not in our list. A is not in our list. So we're going to label it as discovered. We'll put the A in here. And then we're going to label A's parent as the value of V, which is B. So A's parent is B. And then we're going to NQ W, which is A. So we need to add it. And remember, it's a Q, so we're going to add it to the back of the Q. So we added, well, we have to add W to the Q, which is A. We're NQing W, which is A, so we're adding that to the back of the Q. So now we go back up to the for loop and we recall that have we processed all the edges from V, which is B. So we processed B to E, B to C, B to A. So yes, we've done all three edges from B. So we're finished with this for loop. We go back up to Q and the while loop here, and we ask while Q is not empty, and it's got two things in it. So we're going to DQ, take something off the front of the Q and put it in V. So we're going to take the C from the front of the Q, and A will then move up to the front of the Q, and that C will go in V. And we ask the question, is C the goal? And no, the goal is the end node A, so C is not the goal. So we want all edges from C. C has two edges. C has an edge to B, and C has an edge to A. So we want to remember those two edges. So then what we'll do is let's consider the one from C to B. So we're considering the edge from C to B, and we're going to ask the question, is W not labeled? And we notice that the value of WB is in the discovered list. So it is labeled as discovered. So that means this is false, and we're going to skip all this in the if statement. We go back around and consider the next edge from C. So that would be C to A. And we do the same thing. We ask if W is not labeled as discovered. Well, A is also in the discovered list. So that means this if test fails. We go back to the for loop, and that means we've processed both of the edges from C. We processed C to B and C to A, and we didn't want to backtrack, so we didn't do either one of them. So now we finish with this for loop, and we go back up to the Q. Is the Q not empty? And that's true. The Q is not empty. There's A and A in it. So we DQ A, and we put it in V. So A is going to get removed from the Q and put in V. And now we ask the question, is V the goal? And it is, so we return it, and that just causes this search to stop. We return from a function that causes the search to stop. And so we've completed the search, we've visited all the nodes, we've traversed the entire graph, we've visited all the nodes, and we've come up with this parent map. And how is this going to help us? Well, if we start from the end node and look in the parent map, we can see we get A to B. And then if we take the parent of A and look in the parent map, we get B to E. And then if we look at the parent of B in the parent map, we get E to D. And if we look at the parent of D, we get D to F. So what this gives us is a reverse lookup of the path from F to A. So it'll take a little bit of extra processing to convert this parent map into a nice path, but I think you can see that we've found a path. If we go from the end node and find its parent, and then take that node and find its parent, and then take that node and find its parent, and continue, we end up finding a path that goes from F to D, D to E, E to B, and then B to A. So we've actually found a path in our graph. Now, it may not be an optimal path, it may not be the shortest path, but we have found a path, and that's how the breadth first search works. Look back for a later presentation. We'll actually implement this, add this to our graph class, and see how this might work in an actual program.